Hello, I am Vijay John Gerson from the Department of Chemistry. Today, we are going to deal with an experiment in thermodynamics called Joule Thomson's porous plug experiment. This experimental device is designed in order to study the thermodynamic variations of a gas when it flows through a porous plug. And in this experiment, we have a thermally insulated pipe fitted with two pistons on both sides. And this is separated by a porous plug through which the gas can be passed through. And in the first chamber, the thermodynamic properties of this gas is P1 pressure and V1 volume and T1 temperature. And in the second chamber, the thermodynamic properties are P2 pressure and V2 volume and T2 temperature. And remember that P2 is always less than P1 and T2 is always greater than T1. And we assume that this experiment is carried out at constant enthalpy, that means delta H is equal to 0. And in the beginning, let us assume that this piston is close to the porous plug and all the gas is in the first chamber. Now, apply a pressure in the first chamber so that some of the gas it can be passed through the next chamber through the porous plug. Now, uh, in chamber 1, work is done on the gas, but in chamber 2 work is done by the gas because the piston is moving this side. Now, in both cases, a definite quantity of work has been done, and we assume that work done on the system is always positive and work done by the system is always negative. That is the sign convention in thermodynamics. Now, let us consider the chamber 1 and the work done in this chamber by the system as W1, and it is positive P1 V1 because it is a pressure volume work. Now, consider the second chamber where the work done is W2 and which is minus P2 V2. Now, if we want to calculate the net work done in this experiment, we can calculate it as W is equal to W1 plus W2, and substituting the values of W1 and W2, we get P1 V1 minus P2 V2 is equal to W. Now, let us consider the internal energy change during this process represented by the mathematical expression delta U is equal to U2 minus U1. Now, since Joule-Thomson experiment is carried out adiabatically, the Q term in the first law equation become 0 and the first law of thermodynamic equation become delta U plus W is equal to 0. And if we rearrange this, delta U is equal to W. And this W can be uh, positive or negative. And as it is the net work done, both the components are there. That is why we never use a sign convention for W. Now, expanding this equation, we get U2 plus P2 V2 minus U1 plus P1 V1 is equal to 0. And you know that U2 plus P2 V2 is equal to H2, that is enthalpy of the second system, and U1 plus P1 V1 is H1, that is the enthalpy of the initial system, and that is equal to 0 according to this equation. That is why we assumed that delta H is 0 during this Joule-Thomson porous plug experiment. And those experiments in which the delta H becomes 0 is called isenthalpic processes. that is another important term in thermodynamics, is enthalpic processes where delta H is equal to 0. Since H is a state function, we can assume that dH is a complete differential. And taking H as a function of pressure and temperature, we can differentiate it as per equation 1. Dou H is equal to dou H by dou P at constant temperature, and dou P dP plus dou H by dou T at constant pressure dt. And we know that this term dou H by dou T at constant pressure is equal to the heat capacity at constant pressure Cp. So substituting Cp in equation 1, we get dou H is equal to dou H by dou P at constant temperature dP plus Cp dt. And for an adiabatic expansion, delta H is 0. And this term becomes 0 as per this explanation. And therefore, equation reduces to dou H by dou P at constant temperature dP plus Cp dt is equal to 0. That is equation 2. Rearranging that equation 2, we get Cp dt is equal to minus dou H by dou P at constant temperature dP. And again, taking dP this side, we get dt by dP is equal to minus dou H by dou P at constant temperature divided by Cp. And equation 3 can be written in this format also. Dou T by dou P at constant enthalpy is equal to minus dou H by dou P at constant temperature divided by Cp. And in this equation 4, this term dou T by dou P at constant enthalpy is called the Joule-Thomson coefficient, which can be expressed using the term mu J comma T. And in Joule-Thomson coefficient, it can be directly measured if we know the temperature change and pressure change in the experiment. So we can calculate the Joule-Thomson's coefficient mu Jt using this equation. Mu Jt is equal to delta T by delta P at constant enthalpy. So where delta T is the change in temperature, delta P is the change in pressure during the process. And coming to the significance of this Joule-Thomson coefficient, we can say that if the value of mu Jt is positive, a corresponding cooling takes place when the gas passes through the porous plug. And the reason why cooling takes place is that in the beginning we assumed that P2 is less than P1. So P2 minus P1 will be always negative in this equation. That is, delta P is always negative in this equation. So when mu is to have a negative value, delta T value should also be a positive value. Therefore, we get a positive value for mu Jt, and that is why the cooling takes place since delta T become negative during the cooling process. Now, coming to a negative value for mu Jt, that is, if we get a negative value for mu Jt, that means warming takes place when the gas passes through the porous plug. That is, again, we know that delta P is negative in the denominator, and delta T in the numerator should have a positive value in order to have a negative value for mu. Therefore, a negative value for mu Jt will always correspond to warming. Now, there is another situation where the value of mu is 0. That means at that temperature, there will not be any change in delta T and delta P. Therefore, neither cooling nor heating takes place during that process, and that temperature at which no cooling and no warming take place is called the inversion temperature. And that is about the uh, Joule Thomson porous plug experiment, which is used to study the thermodynamic changes or temperature changes of a gaseous system, or in general a fluid, when it passes through a porous material. Thank you.